Well, first of all, I'd like to thank for the invitation and thank Jatin for being here and inviting me to come and speak to you. I work at the Energy Planning Program. It's based in the Graduate School of Engineering, and we mostly do work with energy, but we also have a lot of work on environmental issues related to energy systems. And I am more closely interested in climate change. All three aspects of it, impacts, adaptation, and mitigation. So I'm going to talk a little more about that. But first of all, I'd just like to present some of our research team, because all of this work, you never do it on your own. So you have your advisors, you have people that work with you, and we have a very good team of PhD, masters, and postdoc researchers. And of course, my two advisors and a very good colleague of mine that have also been involved in a lot of this work. So our department has about 12 professors, so it's not a very big department, but we have done a lot of work, and we have been very, very successful in Brazil, and we have been maybe the top energy program in the country. So this is something that we want to keep doing, and one reason we have this such a good. So the reason why we do a lot of research is because we have a lot of connections with people like abroad. We have people that work closely in Berkeley, in Maryland. So one of the reasons I'm here, which is actually nice, is to make connections. So I hope that at the end of this talk we can have, maybe change some cards and keep this relationship closer in the future. So just a brief summary of my presentation. I'm going to talk a little about the Brazilian energy system. For those of you who are not acquainted with it, it's kind of similar to the Canadian because it's very much based on hydropower. So this is something that a lot of the stuff that I'm going to be talking here actually can have similar issues to the Canadian energy system because of the high dependence on hydropower. And then I'm going to present two case studies that we have done in the past on climate change. So basically, one is the economics of climate change in Brazil, which was a very pioneer work that we did back in 2008 and 9. So basically what we did was we looked at how climate change could affect the Brazilian energy system. That means, so everyone talks about climate change and that it's a problem. And why is it a problem? It is a problem because once we have different rainfall regimes or higher temperatures, that's going to create impacts on both natural and human systems. And the systems that we have been studying is the energy system. So how would, for example, lower precipitation levels affect the hydropower production in Brazil? How would a temperature increase maybe reduce the thermal efficiency of a natural gas plant, or maybe even increase the demand for cooling in the household sector, which in turn would actually increase the need for supply of energy. So these kind of issues that we have studied in this project. And the other one is mostly focused on mitigation, which is looking at what are the possibilities, what are the options to reduce greenhouse gas emissions in the energy sector. That means how can we maybe substitute fossil fuels for other fuels? How can we increase energy efficiency, and what is the cost of all that? So what we basically did here was we went through all the sectors in Brazil and looked at the mitigation possibilities that was available for these sectors and calculated the costs of those measures to come up with low carbon scenarios for Brazil for a given, let's say, price of carbon. And then I'm just going to quickly talk about some other projects that we have been doing in the Energy Planning Program and what I'm doing right now at the Joint Global Change Research Institute, which is a collaboration between the University of Maryland and the Pacific Northwest Laboratory in the United States. I've been there for two months now as a visiting scholar, and I'm just going to talk a little about the work I've been doing there. The Brazilian energy system is very peculiar. And the reason for that is because it's mostly renewable. 44% of our total primary energy is renewable. So this is quite a large share. If you compare to other countries, it's much lower than this. Maybe it doesn't go as high as 10% in a global average. So all these 44%, it's mostly related to hydropower, which accounts for around 80% of our electricity. So 80% of the electricity supply in Brazil in 2011 was actually came from hydropower plants. But also we have a lot of sugarcane, which is something that it's particularly difficult for us to model because it's a product that gives out a lot of different energy carriers. For example, from sugarcane you can actually brew ethanol, and that actually accounts for 15% of our transportation sector fuels. In fact, in Brazil, 25% of our gasoline is actually ethanol. Our gasoline is blended. So we have a high share of renewable energy also in the transportation sector. But sugarcane ethanol can also give, so once you squeeze the sugarcane and get the juice, you ferment and get ethanol. But the straw can actually be burned to generate electricity. And around 6% of our electricity generation actually comes from sugarcane bagasse, it's what we call it. So it's also something very, it's a big renewable source in Brazil as well. And Brazil also has a large wind potential, but it's not very exploited yet. So we have a lot of wind power in the northeast of Brazil, also in the south, in Rio Grande do Sul. We haven't got a lot of wind turbines installed yet, but it has been growing a lot recently. I'm just going to show you some graphs on that. So I just added this slide in the last minute because I knew I was coming to Canada, and it's just from the International Energy Agency World Statistics. So this is just the major hydropower producers in the world. And as you can see, there's China in first, and then there's Brazil, and there's Canada. So we are the biggest hydropower countries in the world. But one thing that is actually different, Brazil is different from Canada, is when you come to this table here. This is total electricity generation, which is in terawatt hours. So Brazil is just a little above Canada. But if you look at the electricity generation as a share, so then Brazil this is kind of outdated, but 2001 was 80%. 80% of our electricity was actually came from hydropower plants, whereas in Canada it's 57. It's a large share still, but when you go to a very, very high share, like Norway is 94, you start to have some problems with intermittency of hydropower. Let's say if you have a drought, then you're in trouble. We actually have had issues with that in the past, and what happens today is that we have a very big backup capacity of natural gas to in case the rain doesn't come and the hydropower just is not enough to supply our demand. So this is the Brazilian energy matrix. So as I said, 44% is renewable. Of course, and then sugarcane is a big part. Hydraulic energy as well. Wood and charcoal. I got this from the Energy Balance, and they actually put wood and charcoal as renewable, and we know it's not 100% renewable. I'm being honest with you. So I'd say that some of this is from deforestation, but most of it today, I mean, in terms of large-scale consumption of wood and charcoal for, let's say, for the steel industry, for the paper and pulp industry, it's mostly renewable, but it's not 100%. And others, such as wind, black liquor, and some other sources, 4.1%. And of course, we have oil as the biggest source, just like anywhere else in the world. We have some natural gas, but we don't have much coal. So Brazil doesn't have a lot of coal. There's some mines in the south, but the quality of the coal is very poor. So we have about maybe 20 plants of coal power plants in Brazil, and it's not a big share of electricity generation, mostly because we don't have a lot of coal mines in Brazil. We have 2 nuclear plants in Brazil, in the state of Rio de Janeiro. We're building a 3rd. So that's going to increase that share maybe to 2% in the future. It's supposed to be ready in a few years. So there's not a lot of nuclear energy in Brazil as well. So I looked at the Canadian numbers, and so in terms of electricity generation, these 2 are bigger. This is the big difference between Brazil and Canada. So these 2 are around 15% from what I get. So that kind of gives you an idea of the differences between the Brazilian energy system and the Canadian energy system. So this is electricity generation. As I said, 82% is hydropower. Natural gas is very small. This is all biomass. This is all sugarcane bagasse, which is also relatively big. nuclear, oil products, coal, and wind is only 1%. But as you can see, wind has increased a lot in the past few years. This is 2005, this is 2011. So wind power generation is still small, but has been growing recently. And if you look, I'm going to show you a slide in a minute, the long-term plans, the official long-term plans, they actually foresee a high penetration of wind power in Brazil. So the way that the electricity generation, the electricity options are hired in Brazil is through auctions. And recently, wind power has been competitive enough to compete with natural gas and other sources that are supposedly to be cheaper. So wind power has been becoming more and more competitive, and there has been a lot of wind farms being installed, specifically in the northeast Brazil, but something in the south as well. So this is a map. This is a map of a country, and the colors are actually river basins, the major river basins. So this is actually a map of all the hydropower plants that are in the interconnected system. There are about 200 hydropower plants around here, so it's 159. So this is all the major hydropower plants. There are actually around 600 hydropower plants in Brazil, but most of them are very small, so they're not actually interconnected to the grid. These are the ones that are actually interconnected to the grid, and these account for around 90% of the electricity generation from hydropower, so this is what we want to look at. So most of our electricity generation from hydropower is actually located in the Paraná Basin, which is in the south of Brazil. It's just there. So you have big power plants like Itaipu, it's 14,000 megawatts. We have a lot of power plants that are above 1 gigawatt of installed capacity, so they're very, very big hydropower plants. If we look into the future, then most of our remaining potential is actually located in the Amazon region, which is somewhere around here. We have now 3 power plants that are being built there. It's called, 2 of them on the Madeira River. One of them is 3, the other one is 4 gigawatts, so they're pretty big. And we have the controversial hydropower plant of Belo Monte. I don't know if you have heard of it. It's going to be the 3rd biggest in the world. It's 11,000 megawatts of installed capacity, actually built in the Amazon region. So there has been a lot of debate on whether this power plant should be built because of local environmental restrictions. And I don't want to go into the merit of that discussion, but one thing that I would like to point out from that discussion is that Brazil has a very renewable energy matrix, specifically if you're talking about electricity generation. And as we go into the future, we know that we have a lot of potential for hydropower generation still in the country. I can say that just in the Amazon region we would have we could just double our hydropower generation if we just took everything that was available for us in the Amazon region. But that's simply not going to happen because of local environmental restrictions. So this is one consequence of it. So of the around maybe 200 gigawatt that was left of hydropower potential in the country, maybe we won't get as far as 50 or 60 in the future because of local environmental restrictions. But one other consequence of the local environmental restrictions to hydropower construction in Brazil is that we're going to have small reservoirs. So the power plants that are being built now in Brazil, they have been built with a lower reservoir, which means they have a lower capacity to regularize the generation throughout the year. So they have a lower ability to cope with seasonal variations. And in that case, we'll have a lower capacity factor. We will have not as much energy from those power plants. And those power plants will become more vulnerable to droughts and other maybe extreme climate events like the ones I'm going to talk about in a few minutes. So these are the consequences of the local environmental restrictions. I'm not saying that we should not build or we should build hydropower plants. I'm just saying that this debate has actually made it clear that hydropower is going to have a limit at some point in Brazil. So when you have such a high penetration of hydropower, you need some way of backing it up in case you don't have enough rain. So in that case in Brazil, what we use natural gas. So this is what happens when so back in 2001, we had a power shortage because of a drought. And at that time, we didn't have enough natural gas capacity to cope with the intermittency or maybe an extreme event in hydropower generation. But now we actually have a big capacity of natural gas. I showed you the numbers. Natural gas generation was around 4%, but the installed capacity of natural gas around more than 10, which means that the natural gas is just sitting there for backup. So what happens is, if you can, to attend current demand, you can actually use hydropower or burn gas. But if you use hydropower and then it rains, then you're good, because you're going to refill your reservoir. But if it doesn't rain, then you have a problem. So then natural gas comes as a backup to hydropower plant in Brazil. So what we call when you in the literature, when you refer to the Brazilian energy system, you don't say it's a hydropower system. You say it's a thermal hydropower system, because the natural gas has an important role in compensating for extreme events and being there as a backup for electricity generation in case we don't have enough rain. One other particular thing about Brazil is that it has an interconnected system that's spreads throughout the country, and this is very important for the country, because this is where most of the hydropower generation capacity is the blue circles. This is the power plant that's being built in Rio Madeira. Belo Monte is going to be around here. So these are future lines that are going to be built. So what happens is Brazil has an interconnected system, and it's such a big country that at some point it might be raining here, but it's not raining here. So what you can do when you have such large interconnections is you can just send energy up or down according to seasonal variations. In fact, the seasonality of hydropower production in the south complements the rest of the country. So back in 2001, when we had the energy crisis, for example, we didn't have this. So we had a shortage in the northeast, but we had surplus in the south. So we were actually wasting energy in the south because we couldn't just send energy up north through the transmission lines. So this actually helps to make the best use of our hydropower potential. So if it's dry here but it's wet here, we can just send energy up or down according to the seasonal variations. So this actually increases the amount of the energy you can get from the system by around 10% in average, according to some studies. So this is just the seasonality of the flows. So as you can see, the south is very much complementary to all the other regions. And by making the use of these interconnections, you can actually make the best use of that. One other interesting thing about Brazil is that in the northeast Brazil, we have complementarities between wind and hydropower. So this is the energy stored in hydropower reservoirs, and this is the average wind production. So as you can see, it's windy when it's dry. So this is very good for Brazil, because then if we have a big wind power generation park in the northeast, then you can actually compensate from some seasonal variations in hydropower production. It is a good match that we have in the northeast of the country. So this is it's not exploited yet, but as I mentioned, wind power is becoming more and more important in Brazil. So this will be something that's going to help us attend to our demands with using energy, renewable energy in the future. So just a quick look into the future. This is the official 10-year plan, which is looking to 2021. As I said, there is supposed to be a big increase in wind energy. Sorry, I couldn't translate that from Portuguese. This is wind. This is biomass. This is small hydro. This is thermal. This is nuclear, and this is hydro. So there's supposed to be an increase from 1% to 9% in wind energy. This is official projections. As I mentioned, people are expecting a lot of wind energy in Brazil in the future. Not as much in biomass, and even hydropower has a smaller capacity in the future mostly, but this is all proportionate. So one quick comment here. This is 72% because this is actually installed capacity and not electricity generation. So because hydropower has a lower capacity factor, then it has a more installed capacity than actual. No, this is actually generation, I'm sorry. I'm done talking about the Brazilian energy system. So now I'm going to just quickly talk about two studies. So this is an early study we did in 2006, which is Brazil, a country profile in sustainable energy. You can just Google it, you find it if you're interested. So I'm not going to talk about this one, but I just pointed it here because it was the first step into a lot of different research projects that we have been doing in the past. So by then, what we did in this report was we just projected energy matrix scenarios for the future, which is actually something I just presented to you, but it's been done by the Energy Planning Agency now. At that time, the Energy Planning Agency didn't exist. It was created after that. And since then, it has been doing the energy plan, the official energy planning for the country. So since we are at the university, we need to think about new things to do with our research. So we just went on to do some climate change analysis. And this is a report that came out in 2008, which is the Economics of Climate Change in Brazil, where we assessed impacts and mitigation, in impacts and adaptation in the Brazilian energy system, according to some climate scenarios from the IPCC. And this is a report that we worked on in 2010, which is the low carbon scenarios for Brazil, in which we looked at all the mitigation alternatives in the country and looked what were the costs and potentials for all those alternatives. So I'm going to talk about these two here in more detail just now. So in this study, we actually gave a very comprehensive look on the impacts that climate change could have in the Brazilian energy system, but I'm not going to talk about it all. I wouldn't have time to do that. But what we did, we looked at how climate change would affect hydropower production, energy demand, biofuel production, wind energy, and thermoelectric production from natural gas. So it was a very comprehensive study. I'm only going to show you the results for hydropower, because they are, of course, the most relevant because of the nature of the Brazilian system. So just a little background. The problem with climate change is that if you have changes in the climate patterns, you'll have a difficulty to plan ahead things that you have been doing with the kind of climate you're used to. What I mean by this is that when you plan your energy system, you have to think about energy prices, energy demand, and you have to think, when you have a lot of renewables, for example, what's going to be the climate. As I said, if it rains, then you're good. If it doesn't rain, we need to have natural gas to compensate. So climate change, by changing the behavior of climate, it can actually make that choice more uncertain. You have to plan ahead maybe to a higher variability of climate, for example, or higher temperatures. So in that case, one thing we did was that we looked at some scenarios from the IPCC and did a what-if analysis, let's say. So let's suppose climate change is going to increase temperature by how much and decrease precipitation by that much. Then what's going to be the impacts on hydropower production? And more than that, we then looked at what would be the best alternatives to compensate an eventual decrease in hydropower production in Brazil. In that case, I'm talking about adaptation. So there is a procedure to do that. This has been revised. This is this is the way people have been doing climate change assessments in the past few years, using the sequential approach. More recently, we're doing what we call the parallel approach. I can talk about maybe after the lecture, but this is the methodology we used. Basically, it starts from a greenhouse gas emission concentration. So when we think about climate change, we look into the future and say, oh, the climate's going to increase because we have a higher concentration of greenhouse gases in the atmosphere. But how much higher is that concentration going to be? So that's the first uncertainty we have. And so when we look into the future, the IPCC launched a report back in 2010, which is called the Special Report on Emission Scenarios, that creates about 40 different scenarios for the evolution of greenhouse gas concentrations in the country up to 2100. So based on the concentration of greenhouse gases, there are a bunch of models. There are about 20 general circulation models throughout the world. These models, they are basically simulations of the Earth's climate. They are computable simulations of the Earth climate. So they are massive models. They run for a long time. They're very complex. And because of their complexity, they actually look at the Earth in blocks that are very coarse to regional analysis. For example, a general circulation model that we used, the Hadley Center at the time had a horizontal grid of 300 by 300 kilometers. So that's very coarse. And so what we did, we needed to downscale that result. And that was done by the Institute of Spatial Analysis in Brazil. So we actually got downscaled results from DCMs by the INPE. Downscaling is actually reducing that grid level from 300 kilometers, let's say, to 20 kilometers. Today, the GCMs are becoming more and more detailed. So recently, the new GCM runs are actually more precise in their regional level. So maybe some of them go down to 20 kilometers. But not at that time, we needed to do some downscaling to actually have it in the regional level. And this is actually where we start. So we'd use our models to assess impacts of how much, given a variation of precipitation and temperature, how much that would affect the energy system. And then we did some modeling as well to see how would the system adapt to an eventual impact that was projected here. So one thing that we need to be sure of when we talk about this is that there is a lot of uncertainties. And these uncertainties build up out across this chain of modeling. So for a start, we don't know what's going to be the concentration of greenhouse gas in the future and what the impacts of those concentrations are going to be at the global level, at the local level, and even our own modeling for energy system has our own uncertainty. So this is a lot of uncertainty, so we need to be careful what we say here. It is actually a scenario development and not a projection. So when we had all these different scenarios for climate, we had to choose. So we chose actually the one that was the Hadley Center, and it's highlighted here. This is temperature and this is precipitation changes. And as you can see, the Hadley Center model is the one that projects the hottest and the driest climate for Brazil. So that's the one we used. So we wanted to have a pessimistic scenario. We wanted to have the worst case scenario. So what's the worst projections for climate change in Brazil? That's the Hadley Center, so that's the one we used. And as you can see, the north and northeast of Brazil in the Hadley Center model is projected to have a very, very large decrease in precipitation in the future. This is the 2010 to 2040, this is 2041 to 2070, and this is 2070 to 2100. So by the end of the century, the Hadley Center projects a lot of dry weather in the northeast Brazil. So I just wanted to highlight this because the results are all going to be based on this scenario. And as you can see, it's very pessimistic. So we use some hydrological models to translate variations in precipitation and temperature into river flow. And then we use the hydropower model called the Assutio, which is it's a model that simulates all those 159 plants individually, and it operates it according to exogenous river flow inputs. So what we did is we used a hydrological model to see how would river flow would change, and then we add that to the model. And given the new river flow regime, what would be the energy that we would get out of it? And that model gives you actually two measures for energy, the firm energy and the average energy. The firm energy is the amount of energy you can get in the worst hydrological scenario, is the highest amount of energy you can get 100% of the time. And the average energy is just the energy you can get on average hydrological conditions. So this is average energy. As you can see, the model shows very dry conditions in the north. So actually there's a decrease in hydropower production here. This is by river basin, aggregated by river basin, but not in the south. And as in the south, you have most of the installed capacity. In terms of average energy, that didn't matter much for the country because we can just send energy up. But that's for average energy. That means the average hydrological conditions. But when we look at the firm energy, which takes into account the driest seasons of all, so in that case, we're looking at the worst case scenario, then even the south is not enough to compensate. So even the south has a decrease in firm energy. In that case, so we have a very large decrease in the amount of energy you can rely on in Brazil if that pessimistic climate scenario would actually happen. So these are the numbers. So as you can see, in terms of average energy, it's not a big decrease, but in terms of firm energy, it goes down as 30% loss. So although in average, you wouldn't have a problem, the driest season, the driest periods would have 30% less energy for you. So that means you would have to have more installed capacity to compensate that. So this is what we did next. We just used our model, MESSAGE, which is a supply optimization model, to actually evaluate the least cost adaptation strategies for that loss in hydropower production. So the good thing about MESSAGE is it's an integrated model. So you can actually look at all the energy chains, natural gas, coal, oil, sugarcane. So even if we look at the impacts on hydropower, you can get second-order effects into other energy chains, for example, in the oil sector, for example. And since it's an optimization model, we know that the adaptation measures that we find in MESSAGE, they're going to be least cost. So what we basically did was we had two scenarios, and we run the scenario with no impacts and see what the system would be like. And then we just decrease the amount of energy from hydropower that we would get and run the model again and see how would the model respond to that and see how much more capacity would build and based on what kind of energy sources. So the results were, of course, hydropower would decrease because of that's what we did. We decreased the amount of hydropower available to us. But what we got was a big increase in natural gas as well as wind and some other energy sources. So these are supposed to be least cost options because it's an optimization model. So this is for the B2 scenario. And just a quick discussion about the results is that decrease in hydropower production would cost us about $50 billion to replace in case that scenario would actually happen. And because natural gas was being used by other sectors, we would have to displace the natural gas from, let's say, industry, and in which case it would be replaced by fuel oil. So that was our impacts and adaptation study. Now I'm going to talk a little about the mitigation study. So basically what we did was we compared two scenarios. The official scenario for the evolution of the energy system to 2030, which was built by the Energy Planning Agency. And what we did was, given that technological and energy mix that they planned, what would be the alternatives to each specific sector to replace into best available technologies and they'll decrease the emission of greenhouse gases. So basically what we did was, this is the amount of energy that the official plan was projected. So we did approach based on wedges, which is every sector has that much mitigation if you take into account those possibilities of substitution of technologies or fuels. And then we compared with the official scenario. So this is just a big summary of results. Total emissions is around 1.8 billion tons of CO2 that the total potential for emission reduction, most of it in the industrial sector. This doesn't take into account deforestation. This is just energy, okay? So if you look into that's a better way to look at. So this was the official energy plan. And these are the wedges of emission reduction that we can find in the industrial sector. You're probably asking, what's this? This is replacing deforestation charcoal with renewable charcoal. This is just planted forests. So we parted from the assumption that if we plant a forest today, it's going to take a few years to grow, and then you can have mitigation. So this is actually replacing deforestation, wood and charcoal from deforestation. So that's actually the biggest wedge for emission reduction in the country as of now, as projected by the official plan. So this is the emissions by state. Of course, most of the reduction is in the southeast and south regions where most of the industrial capacity is installed. This is by sector. So this is the cost. So just a quick look. This is actually better to look in a graph, which is easier to understand. So each of these numbers are a different measure. So let's say this could be fuel recovery, energy efficiency, for example. As you can see, assuming, let's say, an 8% discount rate, most of those mitigation alternatives actually have a negative cost. They have they would yield a profit in the long term. So then you would ask, so why is it not being mitigated then? Because, of course, we have a lot of market barriers. And one big market barrier in Brazil is the actual financial access. So an 8% discount rate is very optimistic for Brazil. So if we actually look at the industrial sector discount rate and the access to credit, that wouldn't be the case.
Do you have a list of the 1 to 17? What sorts of things they are?
Here they are. So improving combustion, heat recovery, steam recovery, new process, solar heating, recycling of materials. This is just for the industrial sector. Fuel substitution, coal to gas, or gas to renewables. Eliminating non-renewable biomass, that's the biggest one. Also some cogeneration, because the official plan then, the old official plan we based on, didn't foresee a lot of wind power. So we actually added wind power as a mitigation alternative then. That wouldn't be the case with the new projections. And for the household sector, it's mostly related to energy efficiency. For the commercial and industry, also most related to energy efficiency. We also looked at GTL. Of course, this is not economically viable. GTL is gas to liquids. So using actually gas from flares in offshore oil productions and synthesizing synthetic diesel with natural gas. So this is pretty expensive, but it would decrease a lot of flaring from offshore plants, and a lot of some options also in the oil refining sector. So the total cost of abatement would be $173 billion to decrease that total of 1.8 billion tons of CO2. So that would be the average abatement cost for Brazil. So that was the mitigation study. So that was done back in 2008. So it was published in 2010. We are just starting a new project now that is going to redo that all over again. And one of the reasons we want to redo that is, first, we need to update everything. Second, we want to look into an integrated perspective of mitigation. Because when we look at wedges like those, we're not sure that you can just like add that mitigation potential altogether. I'll give you an example. If you have two different options, fuel substitution and energy efficiency, and each of them give you a total potential of mitigation, but in the end, energy efficiency actually reduces the amount of energy you use, so it decreases the amount of fuel substitution you would have, the amount of mitigation we get from fuel substitution. So these wedges are not, you can't just add them. So what we need to do now, besides revisiting that, updating, we need to put that all together in a single framework to see what would be the actual mitigation potential. So we have done some mitigation. This is just some new studies that we have been conducting at the Energy Planning Program. We have done the same study I just presented on mitigation to the state of Rio. There was a study on how we could use plug-in hybrid electric vehicles to use some of the wasted wind energy we would have in the Northeast to cope with wind power intermittency. We have used our models to test different alternatives of including solar power into the energy matrix, both solar photovoltaic or CSP. We have also done some analysis of the impacts of carbon taxes on the Brazilian economic sector. Let's say, how would the competitiveness of Brazilian industrial sectors change with a carbon tax? There is some work that people do in our department on CCS. We also do some work on distributed energy, electricity generation options. Recently we have been doing some climate change impacts in the Amazonian energy system, which is something relevant because most of the hydropower potential is in the Amazon. And now, looking forward, we want to do some integrated modeling of Latin America. We just started a new project now called Climate Cap, which is actually in a collaboration between different countries. It's sponsored by the European Union. So we're actually going to look at how could we have integration of energy system throughout the Latin America and what would be the gains of that. And of course, we need to update our marginal cost of abatement, which I just spoke about. So just quickly before I finish, just quickly tell you what I'm doing in the Joint Global Change Research Institute, which is, I've been there for 2 months now. I've been working mostly on this model called GCAM. It's an integrated assessment model. It projects energy, land use change, industrial processes, economics into 2100 throughout the globe. And so in GCAM, there are 14 regions. Latin America is one region. I'm there helping them to break up Brazil as an independent region from the rest of the model so that we can actually use use GCAM, the model GCAM, to our own research interests. I'm also working in this Latin American modeling project, which has to do something with the Climate Cap, the project I told you about. Is a collaboration between different countries that are just looking into energy integration in Latin America. And LAMP, the coordinators of LAMP are actually based in the Joint Global Change Research Institute. So this is something I've been doing there as well. And of course, last but not least, my work there is also to make connections, which is the best, has to do with something I'm doing right now. I came here actually to build connections, and it was actually very timely that I got this invitation because I was just just outside DC, building connections, and I got to come here and build some more connections, and I'll go home with maybe some interesting contacts for future research together. So I think that was what I had to say. So if you have any questions now.
Thank you for your remarks. Yes, we have time to take a number of questions. Yes.
So I have a question around how demand is built into the model.
Which one? Which model? GCAM or message?
Do all of your models have demand built into them? Okay, so any of them. I'm just curious because I would say two of the biggest differences between the Brazilian energy system and the Canadian energy system. Brazil had pretty much the population of Canada move into the middle class.
Oh right, yeah.
Recently. 30 million people moved into one of the middle class levels. And I would say that there's really large shifts in wealth and consumption patterns. And I was just wondering if you could talk, we don't have that in Canada, those kinds of shifts happening. And Brazil's population is so much bigger that it's on a grand scale. And I was wondering if you can just talk a little bit about that. And I'm sort of curious, for instance, because there's a lot of really different, household, I'm not sure about industrial, but definitely household energy use patterns that I see between Brazil and Canada. There's not always hot water at the sink where you do your dishes, there's not central hot water and those types of things. And I'm just wondering if you can talk about whether you're looking into whether that's projected and if that makes a really big difference in the models. I'm just curious in general because that's such a huge difference between a model we would have here and I think one in Brazil.
Yeah, we have a residential. So when we look at our modeling system, since we do an integrated modeling, we need to project energy demand for all sectors, and residential sector is one of them. So we have a bottom-up model, which is not that bottom-up, but it tries to separate the energy uses, the energy services that are used in the residential sector. Let's say water heating, refrigeration, cooling, cooking, and refrigeration. So those are the services we have.
Okay, and I think even transportation, because the cars in Brazil are a lot smaller than there is a transportation model as well. Transportation model is harder because because of the data availability. We try to project. Ideally, transportation you want to look at the service, which is
tons of cargo per kilometer or passengers per kilometer, so it's very tricky to do that. We have someone working in the transportation sector. He's a very good. But back to the building sector, which is the major difference between Canada and Brazil. When breaking up GCAM, I had that problem. And when we worked back in 2002 with MY8, which was a model from the International Atomic Energy Agency, we had the same problem, which was Brazil has a very particular household consumption. And the differences is, first, water heating. Most of our water heating comes from electric showers. It's a once-through electric shower, and that consumes a lot of electricity, is not efficient. But the worst part is pretty much associated with peak demand, because everyone gets home after work and go and take a hot shower. So the peak demand is actually associated with electric showers in Brazil. So because it's not a lot of energy, but it's a high potency. So it actually it's a very big issue. And the problem with that is because it's very cheap to install. And most of the low-income class don't pay they have a subsidized fees, so they don't have an incentive to replace that. So some programs, for example, in the state of Minas Gerais, some utilities actually have bought solar heaters and just like gave them to communities that paid low-income fees to actually cope with the problem of electric showers. The second is cooling. So we don't have heating, but we have air conditioning. So this is something that some of the international models don't take into account, and we have to take into account. So the highest, in terms of season and energy consumption in Brazil, the highest energy consuming season is summer because of air conditioning. So those two aspects are something that are the major differences. And we have a bottom-up model that looks into services. And of course, the model also looks into mobility and equipment and access to equipment. So we have premises, of course, we're looking into the future, so we need to make premises about how would income inequality change in the future, and what would be the effect of that having more access to appliances, what would be the effect into energy consumption. So we need to make premises about that as well.
I just think there's so many people, if there's a whole lifestyle shift in between a group, it makes a big impact if it's like a large section of the population that all adopt it.
Yeah.
I was just curious about it. Yeah.
So you have, the question embedded here is this. Of course, there's demographics, and there's shifting demographics in terms of income within the, and the rising income. And you've seen that in Brazil, you see that all over the world, in Latin America and Asia and everywhere else. This pressure of upward movement of income, which brings into demand newer services, particularly cooling, air conditioning load. On this system. Do you have that modeled in
Yes.
this as part of the?
Yes, we do. Our residential sector is actually being rebuilt, our residential sector model right now. We have a couple of students improving our past models based on newest information. So this is the thing about modeling. We have to all the time keep improving and getting the new information. And so we do have, so what we do, basically we separate according income classes. And every income class has a profile on appliances ownership. So then you can play with the mobility within the income classes. Let's say the share of the population that belong to each income class.
Okay.
It would seem that Brazil's in a really enviable position because you've got a lot of hydro capacity. You have an expanding and functioning grid. I'm surprised that solar only came up in the last, near the end of your presentation, but of course, that's a technology that's still in its relative infancy. But you would seem to be in a perfect position to blend solar and wind and a few other renewables with your installed hydro capacity. And then combining that with forest management, so you reverse the deforestation, so you can consume all that carbon that's in the air. And, I mean, there's nothing nicer than a forest. Consume it, but you would seem to be in an enviable position because you've got the Central Plains area that I suspect is underutilized with respect to utility scale solar.
Yeah.
Maybe in the
It's-
future you could
the
put
problem-
in that,
the
but
pro-
balance it with your hydro, because
Yeah.
sunny when probably people, you could do a lot of air conditioning off solar, and then when the people are having their showers, do it off hydro.
Yeah, so solar, the best way to use solar energy in Brazil right now is to heat water for the residential sector.
Yeah.
That's the best solution now.
Imagine.
It's mostly electric
Not- so
showers.
Not the PV electric or
No, just like
solar thermal?
solar thermal to heat water
Yeah,
to 50 degrees Celsius.
right.
So that would be like a very big improvement for Brazil as it is. So and it's the cheapest and the simplest of all solar technologies. We have looked into different alternatives for solar generation in Brazil and how would they enter the grid. So what we basically did was, given a scenario for the evolution of the energy system to 2040, let's say, if we just added solar energy, what would be the cost and what would it displace? What kind of energies would it displace? And it would displace hydro mostly, according to least cost options. But the problem with solar is two. First is cost. It's very expensive. The second is Brazil has a lot of solar, but its potential is pretty much concentrated in some regions because in terms of CSPs, particularly, not, of course, photovoltaic, you just like put it everywhere. But in terms of CSP, which is concentrated solar power, you need to have direct radiation. You need direct radiation, not diffuse. So Brazil is kind of cloudy in most regions.
That's why I mentioned the central plant.
So it's the potential for CSP in Brazil is not that big. It's big because it's a big country, but it's not relatively big as one would think. It's big because it's a big country, of course, but and it's pretty far away from consuming centers and everything. So, but we have looked at that, and we have actually looked at possibilities of making hybrid solar power systems, let's say hybrid with natural gas or even sugarcane bagasse. And we also have looked into CSP with heat storage. Kind of you decrease the power available to you, but you can actually regulate throughout the day. So you have less energy, but you have a more regular supply of energy. So we have looked at them all, but the issue is mostly cost. It's pretty expensive still.
But it'll come down over time.
Yeah, it will, but
Any other questions? Yes?
Can you explain, I still not quite sure, so the cost of hydro production, can you,
the cost?
yeah, the cost with like, from, initial investment, big amount, you build a dam, and then
So
span over 50 years, so,
you mean the levelized? You mean the levelized cost?
Yeah, lifetime.
The cost per megawatt hour.
Megawatt,
So it's below $150 a megawatt hour.
what's the price, electricity price?
You caught me there.
Oh, that's
I would just want to see the profitability
Yeah.
for that hydro.
No, you caught me there. But these are the latest hydropower plants. Most of the hydropower plants are pretty old, so they have already
Yeah,
been paid out.
okay.
So about $50 a megawatt hour
Yeah,
for new generation.
for hydropower. The newest, that's the biggest hydropower plants in the Amazon that have a large capacity. The newer plants, besides those, since they'll have a smaller capacity, they will have a higher cost. They're not as much energy. The biggest the hydropower plant, the lowest the cost, the levelized cost.
Because what's like the return for if I invest like 1,000 megawatts capacity of a hydropower plant, what's like 50 years, what's the return? Is high the return compared with other generation?
I'm not sure I can answer you that question out of my head.
That's a very difficult question.
Yeah,
and it
because there's
depends on how
taxes.
the market
Because
is set
people
up.
always
Yeah.
think hydro
No,
is cheapest.
It is. I mean, it depends on how the markets are set up. So if this is centrally planned system, then there will be a social discount rate that they would use, probably 8% or whatever. it
We
is.
work with 10 in the
And
electricity system.
that is the way you do big major infrastructure projects. If it's a completely private sector funded proposition where equity enters, it's a different question. And so it's never that simple. And then private equity folks get in, they want government guarantees for.
Mainly, I think it's from
Yeah.
the money from the private sector.
This is not a trivial question to answer because, and you have transmission and distribution taxes and you have taxes.
Yeah.
And also, some electricity generation options in Brazil, they actually remunerated for not producing. Natural gas, for example. They are paid even if they don't produce energy.
Yeah.
because they're just there for backup. So they have a minimum amount of energy they are paid, even if they don't generate. But if they generate more than that, then they get paid more.
Just not clear about the cost structure.
Yeah, so it's not a trivial question to answer, and especially if you look at the integrated operation, it's complicated.
I'm doing something to valuation of it's purely financial price valuation of the hydro generation assets. I need to know the cost structure, right? I need to properly model the cost in order to pricing any, generating asset, whatever thermal hydro, in order, it's for the investment purpose.
For comparative analysis, you should look at Department of Energy, US EIA published very comprehensive life cycle cost of energy. But even there, you have to peel out the assumptions related to what they are doing in terms of getting to that cost item, and but it's there, it's available. And there are other such studies by the IEA and a number of others that give you a good sense of which is the most expensive, which falls in the middle, and they go through all the options.
What is this would be a complex answer, so simplified answer, what is the public-private ownership mix throughout the energy sector, like generation, transmission?
I don't know the mix exactly, but most of the distribution utilities were privatized in the 90s. There is, in terms of generation, a lot of the old power plants are all public. Eletrobras, for example, which is a national holding. Some state utilities that haven't been privatized, but the newest plants, most of them, they're like private or public-private partnerships. So, but I wouldn't know the number, the specific share of public.
But it's real mixed.
Yeah.
It evolves from country to country. I think, any other questions?
I have
Yes.
one. So can you talk about a little bit about the modeling of long-run river flow?
So the river flow, the hydrological model, or
No,
the
because it's different. I'm more interested in, do you have some simple like diffusing type of model? Do you know that, like model some price process or something? Are you familiar with this?
well, it's if you want to model electricity prices from hydropower production, you can either do an exogenous utility that's buying, or if you do an integrated modeling like we do, you need to take that into account, the complementarity of different sources and the cost of those, and the competition between those. So it becomes much more complicated, especially if you have hydropower, in which if there's a dry season, you add more gas, and in that case increases the price.
Yeah.
So if you have...
my purpose is that I still, from the investment perspective, for example, if I have invested a 1,000 megawatt hydropower plant, right? Maybe that will be built for 100 years or something. I need a very good model for the water flow in order, because water flow is like input, right?
That's...
So I want to know I cannot say, couple scenarios. I want to have a good model to see, what time, how much to produce, right? What's the market price of electricity in order to value that's a big project, 100-year project. I need to have a very good forecast, just kind of.
So that's...
Use time series or whatever,
Yeah.
have a diffusion model. I call diffusion model is like, I don't know if you have heard or not, diffusion model, mean reverting process, you have Brownian motion or something. Like modeling electricity price, it's the type of model.
It's like I said, when we talk about...
It's very complicated, but I just can capture some, based on climate change, can capture some, maybe a regime switch over some time.
Yeah, that's a problem with climate change. Historically, what they do, they still do that in Brazil. They have the hydrological series, the time series, and they build autoregressive models to project them into the future. So they're just using the past to foresee the future. That's what's being done throughout the world, because that is based on the assumption that river flow is a stationary variable.
Maybe in the long run we'll switch to another regime.
Yeah. The problem is when you look in the long run and you look into climate change impacts, then you have to go into GCM modeling, which is, in that case, you have a different variety of scenarios. So as I showed you, some models actually project drier conditions for Brazil. Some other models project wetter conditions for Brazil. So in that case, you have to build scenarios. There's no way you can actually know what's going to happen.
That's okay, because when I build model, I can assume, for example, follow this process, water flow. Another, dry or wet, it doesn't matter. I can build a model, I just input a different input for the water flow process. So,
but you want the model for the price and not for the amount of electricity you get. You want a model for the price or for the river flow?
I already have model for price, because that's pretty well studied. You can use currently popular price process. You use the regime switching model, because you have frequent price jumps. You have base regime. You have vertical process. Another is purely jump process. Sometimes the peaking time you jump to $1,000, right, per megawatt hour. This is pretty well in the time jump diffusion time model. What I talk about is the water flow model.
So there are different methodologies to do that. You can use time series.
Yeah.
You can use hydrologically based models such as water balance models. You can use conceptual models. Each of them has their own level of uncertainty and problems and outcomes. But there is a whole different. There's a whole variety of papers about hydrological modeling in climate change scenarios. That's a very vast literature you can look. But there's basically 3 types of models: statistics, conceptual, and water balance.
Thank you. Any last question? Okay, we would like to thank you for your wonderful lecture and coming to Waterloo.
Thank you.
Thank you.
Thank you.